Yes.
Okay, thanks a lot. And I will start, therefore, with the traditional media. And since this is a meeting on polynomial system solving, I assume that all of you heard about mixed volume, but I want, anyways, to write down that the mixed volume is an operator that takes n convex bodies, or A1 till An, and we can make a Minkowski linear combination of them. And I assume those are bodies in Rn. So we know what this volume is. The TIs are indeterminates. This turns out to be a polynomial. So if we look at the homogeneous term of that polynomial, that's called the mixed volume. This was introduced by Minkowski in 1901 in connection with some geometrical properties of convex bodies, like area of the border and curvature. So I'm writing this because a lot of people sometimes in the community of polynomial system solving, I think I got it wrong. Sorry, I got it wrong. So a lot of people, including myself, mix up things. And okay, I take the nth derivative. I think I need to divide. Yes, I need to divide by factorial n, so that it restricts to the usual volume when the convex bodies are the same. Now, this is also by the famous BKK bound, the number of solutions of systems of the form fi of x equals sum for a in sum ai. That this is a finite set in Zn. So we give a coefficient, generic complex numbers.
Could you write with a slightly larger font?
Okay, I'll try to switch the font. N. So if we count the root in C star n of this sort of system, we obtain factorial n times the mixed volume. So BKK bound says that the number of roots generic is n times v of a1 an, and here ai is just the closure, the smallest convex set containing the support of this equation.
What's
so
M?
wait, what's
M, yeah, M factorial.
n? Here, this is my n. Okay, I simplified this talk. There is no m. So anything that looks like an n or an m is an n. Okay? So
these equations.
So we are interested in solving this sort of equations. So one approach that avoids having to go through Bezout many paths, that is, the Bezout number is just the product of the degrees, that's way too large. So one possibility to do homotopies while staying with the same structure was suggested in, when was that? In 95 by Bern and Berg-Huber. And it amounts to introduce a new variable here and sort of random exponent called the lifting. So when t equals 1, we have the system we want to solve. And if we make t go to infinity, interesting things happen. So the strategy for solving this sort of polynomials usually is first to solve the limit form, then to do a homotopy to a system with random coefficients. That used to be called cheating. Some people don't like this term, but this was coined by D.Y. Lee. It's a good term. And then to solve the true system, and then there are other issues that arise like the endgame. So I want to focus in this talk on this first issue, that is computing not only the mixed volume, but also some structure that encodes what this initial system is, that allows immediately to recover an initial system with all the roots to get the global solution. This step used to be a bottleneck for solving sparse polynomial systems until a series of breakthroughs starting in the year 2000 by Gao and Lee, Gao, Lee and Wu, Mizutani, Takeda, Kojima, and more recently Lee and Lee in 2011. There may be other recent improvements that I'm not aware. Now, all the improvements, all the algorithms that exist for computing this structure that is the lower mixed subdivision are combinatorial in nature. They proceed by exhausting all options. This means that the only complexity bounds that clearly follow from the algorithms, and the only ones that that are known, that I am aware, will be exponential in nature, and this is not the ideal situation. What I will try to explain here is what are the ideas behind a new algorithm that provides also a sort of geometrical bound on the complexity. And the geometrical bound is in terms of mixed volumes. It's not what I really wanted to do. I really wanted to do that the complexity of obtaining this lower mixed subdivision is essentially the mixed volume of the original system. There are other terms that will arise, but overall it's something that is getting closer to get output sensitive. I must remind you that even computing the volume in terms of traditional complexity is Sharpie complete. This is a classical result by Kashijyan. And the Kashijyan result just makes it hopeless to get something that is less than Sharpie complete for computing mixed volume, taking the description of the polytopes as input size. But in any case, if we are going to do homotopy, we will follow all the paths, and this forces us to do as much work as it is the size of this lower mixed subdivision. Also, something that I must say is that I am speaking like if it was just one algorithm, but there are several different algorithms. When I speak on complexity, things depend a lot on the model of complexity. And if I go to practical implementation, I will not do exactly the same algorithm because of numerical issues. This may increase to the cost of the implementation, but sometimes I get, the results will be better than the worst case bound. And now I'll switch temporarily to the computer. And I must say I strongly agree with the email Frank sent us. So the number of slides I will use is 0. So what I will do here
That's a good upper bound.
is to invoke a version of my program.
Can you make your font size bigger than 0?
I can do that later. If, maybe I can do, I may be able to do, yes. Sorry, I forgot. Control plus may work. No, I'm sorry, I cannot.
I think we're going with your talk.
Okay, so I'm invoking a program that I've been working for some time. And I will compute the mix volume of an example that is Katsura 17, and I will leave it running. Then I'm coming back to my talk. So the computer is doing some work. Meanwhile, I will state the main theorem. We don't need the computer for the time being. It's here. Okay. So.
Don't write in the middle.
But side screens. Can you just close it?
I prefer to use this middle board for now because I will need to keep other things in here. So, or maybe you are right. Maybe you are right. Let's try to do. Here is my font large enough.
Yes.
Okay. I will be informal because of what I said about the difference between the theoretical algorithm that counts arithmetic operations and the number of arithmetic operations that I actually do, which is slightly larger per step, but of course I do less steps than the upper bound. But in any case, if we count the number of operations, I will obtain something that the algorithm produces all the cells in more or less in time. There was a lot of talk this semester on finding hay in a haystack. I'm not concerned with this. Algorithms here are randomized, and therefore we need some sort of average that I may explain you later. And it is of the order, and I'm not completely precise on what I'm writing, but I will need to add over certain numbers that I call VD, d equal 1 to n. times S. S will be the input size, the classical input size, the number of monomials times the dimension. So since I am informal, let's put an n of 1. I'll take out this thing. Maybe I can be more imprecise. So there are some logarithms that I'm not counting, and this VD, this is the important term, the geometric term. So I had n convex bodies. Let's add another one that is the sum of them. So VD will be related to the mixed volume. And here I put A1, A, D minus 1, A, and then a ball. There is a constant here that we always forget. There is a factorial n that does not harm anything because it's the same factorial. Oh, wait a second. Maybe I have an n here. I forgot now if this goes in the denominator or the numerator. So if I have this, the coefficient may be made in factorial n ways. Okay, when I wrote the mixed volume here, inside here there is already a 1 over factorial n. So I multiplied back to obtain the expected number of solutions of an hypothetical polynomial system, albeit here I have the ball and not the AIs. And there is an extra factor that I'm bounding by half to the n minus d, but that may be better than that. What is this? The last factor is maybe the most interesting. That's Vn. In the case of Vn, I have the mixed volume of the first d minus 1 polytopes and the last, and at the end, the sum of all of them. So I should tell you more or less how I get here and show you by some pictures how the algorithm proceeds. So I'm using some classical tools. One of the most classical tools in mathematics is the Lagrange transform. So we have a function B that is the lifting. It is defined in the disjoint union of the AI, the supports, not the balls, the support, and goes into the real numbers. Its Legendre transform is a new function from a new space that I will call C space. So let's call it lambda. I can start with doing the Lagrange transform of just one of the components. So lambda I, let's call Bi the restriction to AI. Lambda I takes a number xi, vector xi, a real vector. It's in dual space to the space of monomials, and it takes it to the maximum over all A. So it's dual space, so I should write A xi minus B of A. This is a convex function. I said I was restricting here to the eth component, so this is AI and this is BI. And we can also define lambda from R n to R n takes xi to lambda, where now lambda is a vector. So this is Legendre. I said Legendre or Lagrange. So this is the Legendre transform. I hope I did not get it wrong. So here we have a situation that is very similar, but
You're writing that low is not very good because you moved the podium, the block. Move the board over.
Move the board over.
Move the board over. There you go. But even though it blocks some people.
okay. I'll keep moving.
No, but then you can't see.
Okay, I'll continue on the top. I'll continue on the top. So what we can do with that now is to take the Legendre transform once again. So this is a convex function, convex domain, everything nice. We take a new Legendre transform and we obtain a function B from a I. Let's go on coordinates again. R. So we take x, it goes to sup of x psi minus lambda of psi for all psi, for all psi in the domain. This is a convex function. It's the lower convex hull of the graph of BI, and we can do that for all the other variables. Now, for every value of psi, I draw it in one dimension for the moment. So for every value of psi, there is an extra, in my picture, psi lives here. So for every value of psi, I have to look at the vector psi minus 1. And it attains a maximum at some points in the graph of the function. So I count the number of points, I subtract 1, and I call this number mi of psi equal number of times max is attained minus 1. This is also the dimension of the lower convex hull. I think I'm going too slowly, so let's say that if I fix, let's go to the computer again. Okay, so I need the projection, please.
It's coming.
It's coming.
Yes.
Okay, so let's see. Yeah, something is going wrong.
No.
No.
You need to just press on the, yeah.
Okay. Okay, so now I need to come back and change. So, sorry, I lost my. Okay, just a second then. So I'm Okay, let's look at the polynomial system. So I'll file open, and I'll choose a system like this is Con3. This is a test system, so it's here. Let's solve it. Done. And let's look at the mixed subdivision. So I have to explain what you are actually seeing. I'm just turning here something. The dimension is 4, but I'm projecting on 3 space. You are seeing Xi space. So when the contact dimensions, the mi that I defined, are equal to 1, this means that there are here exactly 2 monomials that survive. This is what we want to find. Those are the so-called mixed cells. The points that are glowing in front of you are mixed cells. If I allow the last mn to drop by 1 eventually, but I maintain that m1, m2 till md minus 1 are larger or equal than 1, then I can still get places where one of the first mi is equal to 3, and then I get other cells that are not glowing. And I can pass from ones to the other by some pivoting. This implies that I have a sum of the mi's that is n minus 1. This is something that is called the tropical curve. And the algorithm worked by exploring tropical curves. So here we are at the top level. We are seeing a certain tropical curve that needs to be explored, and the trouble is that this is not necessarily connected. So I need to wrap up, so I have more pictures to show, maybe after the talk, but then at this point, what I need to do is to show also that besides the complexity bound, I have actual results. This worked in some point. I need to press enter. Okay. So it worked in 613 seconds for an example that appeared to take something like 21 hours in the previous paper by Lee and Lee. Thank you, and I apologize for being out of time. I will not show you the most striking images.
Someone could ask for them. Any questions?
So you can ask me about connectedness. I have an image. You can ask me why it is randomized, and about random flags. I have another picture.
Yeah. So
Yeah.
Why do you use random walks? And they take a lot of time too.
Okay. Let's go back to the previous example. Random walks take really a lot of time, but there is another alternative that brings some complexity problems. Let's see. How do I change here? So this is screen 2. So here I need to explore this graph, which happens to be sometimes connected, sometimes not connected, and in most very big examples it is not. So what I can do is to intersect with an hyperplane, an affine hyperplane. So if I intersect with an affine hyperplane, which is not visible here, but I will make it visible first by increasing the visual radius. increasing a little bit the size of this thing and doing some strange operation. I don't have in this picture. I'm sorry. Let's. I'll make another picture. Open. Let's get the smaller dimensional picture, dimension 3. And now I will do something that I call the full algorithm. So in the full algorithm, you see there is something at the end. Sorry. So this is. I'm sorry. Okay. This is a better vision. So here. There is a plane that is getting close. Okay, so I will perform the same algorithm recursively on that other plane at infinity. We decrease the dimension by 1, and so on. Theorem, each of the spikes of this tropical, here we have a tropical variety curve.
Gregorio, what's the instance? So this is a system of 3 equations and 3 variables? Or?
Yes.
And what's the curve? What's the tropical curve?
So the tropical curve
is in 3 space.
Okay, this is in 3 space, so I want to have 2 points of contact with the first polytope, at least, and 2 points of contact with the second polytope.
So that's the curve that you get by intersecting the first 2 tropical surfaces.
Yes. And then I want to do some recursion, but I need genericity. So I take a random affine plane and cut by a random affine plane. Theorem, every connected component of this curve will cut this random plane at least once. So I go reducing to problems of smaller dimension. The question is that, this number here is the number of mixed cells. Sorry, not of mixed cells. Let's see. It's the number of points of the tropical curve. If I go to the other dimensions, I originally expected this number to decrease, but that's not the case in some very large examples. It increases. And then it decreases again. So in order to avoid that, I use a random search. It works fine, but it has a big disadvantage. That is that I don't know that I am over. So I pay a huge complexity cost. That is what Ioannis has seen in the other listing, just by overshooting. And still, there is no absolute certitude. If I want certitude, I have this theorem that is good theoretically, but that's not enough to get better timing than in the other papers. And then I have some other issues to worry. Here you see those points are very close. This is a common feature. There is a conditioning problem that seems to be structural in some cases. So I need to be careful about numerical stability, and at some point this forces me to send that flag to infinity and use non-standard numbers. But this is another story. Also, there is another reason to send that flag to infinity. That is another picture that I have. It's actually pre-computed. So I'll show you what you will see in a few minutes. I'll call the picture first, and then you may ask me why, because it will take some time to load.
So, as this is loading, let's thank Gregorio again. there you go.
Okay, so what is this? This comes from a model from acoustics, and this is quite typical of what happens in, say, in the center of the amoeba.